Let's get straight to it. HVAC systems are powerful and potentially dangerous. These aren't just boxes that blow hot or cold air, they're complex machines running on high energy, often tucked away in places most people never see. Every day, technicians and engineers work with equipment that can be as hazardous as it is essential. High voltages, pressures, and temperatures mean mistakes can lead to injury or destroyed equipment. A single misstep, like touching a live wire or opening a pressurized line, can have serious, even life-threatening consequences. The risks are real, and they're present every time someone opens a panel or starts a system. That's why safety interlocks are essential. They're the system's built-in bodyguard. These devices are designed to step in automatically, stopping dangerous conditions before they can cause harm. Think of them as the silent sentinels, always on guard. Interlocks prevent disasters by ensuring equipment only operates when conditions are safe. They're not just a feature. They're a critical line of defense, making sure that if something isn't right, the system simply won't run. Too often, corners are cut and interlocks are bypassed, turning a quick fix into a ticking time bomb. It might seem like a shortcut in the moment, but disabling safety features can lead to catastrophic failures, costly repairs, or even tragedy. A proper safety interlock is a non-negotiable rule, not a suggestion. Following safety protocols isn't just about compliance, it's about protecting lives, property, and the reputation of everyone involved. Understanding interlocks is fundamental for anyone working with HVAC systems. Whether you're a seasoned pro or just starting out, knowing how these safeguards work and why they matter should be second nature. This isn't about fancy tech, it's about smart, logical engineering. Interlocks are often simple devices, but their impact is huge. They're proof that sometimes the simplest solutions are the most effective. Interlocks make sure equipment starts in the right order, every time. They coordinate complex sequences, ensuring that fans, compressors, and pumps all work together safely, preventing dangerous overlaps or missed steps. They're the difference between a reliable system and one on the verge of failure. A well-maintained interlock system means fewer breakdowns, less downtime, and a safer environment for everyone. We'll break down what interlocks are, why they matter, and how to spot a proper setup. You'll learn how to identify the right components, test them, and make sure they're never overlooked or disabled. This is about more than comfort. It's about safety, durability, and pride in your work. When you take safety seriously, you're not just protecting equipment, you're protecting people and building a reputation for excellence. In safety, there are no second chances. Let's make it right, every single time, and set the standard for what true professionalism looks like in the HVAC industry. What's a safety interlock? In the world of mechanical and electrical systems, especially HVAC, it's a term you'll hear all the time, because safety is always the top priority. But what does it really mean, and how do we design it to work reliably? A safety interlock is a feature that links two or more pieces of equipment together, making the operation of one device completely dependent on the status of another. This connection ensures that machines only run when it's absolutely safe to do so, preventing accidents and equipment damage. At the heart of every interlock is a simple but crucial choice. Do you use a normally open, no, or normally closed NC contact? This decision shapes how your safety logic works, and it's vital for both safety and reliability. Here's the basic idea. A normally open, no contact is like a door that stays open until you close it. No current flows until the device is activated. A normally closed NC contact is like a door that stays shut. Current flows until you open it by activating the device. So how do you choose? Let's break it down step by step, using practical HVAC examples. Imagine your car's ignition. The interlock only lets you start the engine if the gear is in park. Here, a no contact is used. When the gear is in park, the contact closes, allowing the starter circuit to energize. If it's not in park, the circuit stays open, no start. In HVAC, a chiller won't start unless the water pumps are running. Here, the pump's auxiliary contact is wired as no. When the pump runs, the contact closes, sending a go signal to the chiller. If the pump stops, the contact opens and the chiller can't start, protecting the equipment. But sometimes you want the system to fail safe. That's where NC contacts come in. For example, a boiler's airflow switch might use an NC contact. If the fan fails or a wire breaks, the NC contact opens, breaking the circuit and preventing the boiler from firing. This way, any failure, power loss, broken wire, or device fault results in a safe shutdown. Here's the logic. Use no contacts when you want the system to act only when a condition is positively confirmed, like a pump running. Use NC contacts when you want the system to shut down if anything goes wrong, like a safety switch or emergency stop. For example, flow switches and pressure switches in HVAC safety circuits are often wired with NC contacts. If flow or pressure is lost, the contact opens, and the equipment shuts down immediately. No guesswork, no risk. Always ask, what happens if a wire breaks or a device fails? If you use NC contacts, the system will default to a safe state. If you use no contacts, make sure the risk of undetected failure is acceptable for that application. Step by step, here's how to select the right contact type. 1. Identify the condition you want to monitor: running, stopped, safe, unsafe. 2. Decide what the system should do if the device fails or a wire breaks. 3. Choose no if you want action only when a condition is confirmed. 4. Choose NC if you want the system to shut down on any failure. 5. Double-check your logic with a wiring diagram and test it in the field. Interlocks and the careful selection of no and NC contacts are the backbone of reliable mechanical systems. They're not just a nice-to-have feature, they're absolutely essential for safe, efficient, and dependable operation in any modern facility. That's the foundation of safe HVAC design. By understanding and applying the right contact logic, you ensure every interlock does its job, protecting people, equipment, and your reputation as a design engineer. Safety interlocks exist for one reason: protection. They protect people, like stopping a fan if a technician opens an access panel. In a boiler room, interlocks prevent deadly carbon monoxide by ensuring exhaust fans run before firing. They also protect expensive equipment. A chiller won't run without water flow, avoiding catastrophic damage. A simple flow switch can save a six-figure machine. Interlocks prevent cascading failures. If a pump fails, the boiler shuts down, avoiding explosions. They isolate faults containing problems before they escalate. Interlocks also improve efficiency, like ensuring heaters only run when fans are on, preventing overheating and nuisance shutdowns. This reduces maintenance and increases reliability. Interlocks are life-saving, cost-saving, and should never be bypassed. They're the cheapest insurance you can buy for your system. That's real protection. Let's see interlocks in real HVAC systems. In air handlers, the supply fan must be proven on before heating or cooling elements activate, using pressure switches or current relays. If the fan fails, heating and cooling are disabled, preventing damage. Chillers are interlocked with both chilled and condenser water pumps. Both must prove flow before the chiller starts. If a pump fails, the chiller shuts down instantly. Boilers have strict interlocks. Exhaust fans and dampers must be proven before firing, and low water cutoffs prevent dry firing. Even pumps are interlocked to prevent unnecessary operation and wear. Interlocks ensure equipment only runs when needed in the right order. This saves energy, prevents failures, and keeps everyone safe. The system becomes smart and self-protecting. That's the power of interlocks in action. How do interlocks work? Relays are the key. A relay is an electrically operated switch letting low-voltage signals control high-voltage circuits safely. The relay acts as a middleman. BS sends a signal, the relay closes, and the motor starts. In interlocks, relays enforce the logic. A flow switch wired in series with a relay coil means no flow, no start. Multiple safety devices can be wired in series, creating a chain of permissions. If any safety isn't met, the relay stays open and the equipment stays off. This makes control wiring logical, safe, and easy to troubleshoot. Relays are the building blocks of every interlock chain. They keep systems safe by enforcing the rules automatically. That's how we build reliable, safe HVAC controls. Let's break down the language of relays. Normally open, no, and normally closed, NC, and see how they keep HVAC systems safe. We'll also dive into condenser water cooling tower safety interlocks and AHU high static, low static, and fire damper interlocks, so you know exactly when to use NC and no contacts in your designs. No contacts are open at rest. Electricity can't flow until the relay is actuated. For example, the chilled water pump starter has a no auxiliary contact. This proves the pump is running. When the pump starts, the no contact closes, sending a signal that the pump is actually on. NC contacts are closed at rest. Electricity flows until the device trips. The flow switch in the same system is NC. It stays closed as long as water is flowing. If flow stops, the switch opens and breaks the circuit. The low temperature cutout is also NC. If water gets too cold, it opens, stopping the chiller to prevent freezing. All these contacts, the no for pump run, North Carolina for flow, and NC for low temp, are wired in series to form a permissive circuit. If any NC opens or if the NO stays open, the chiller won't start or will shut down. This same logic applies to air handling units with VFDs. The fire interlock NC, overload NC, and VFD run feedback no are all part of the permissive circuit. If any NC opens, like the fire interlock or overload, the AHU won't run. If the VFD run feedback no doesn't close, the system knows the fan isn't running and will stop. This ensures any failure results in a safe shutdown. Now let's get specific for design engineers. For condenser water cooling towers, safety interlocks are critical. The basin low-level switch should be NC, closed when water is at a safe level, opening if water drops too low to stop the tower and protect the pump. The fan motor overload is also NC, opening on fault to break the circuit. The tower fan run feedback is no, closing only when the fan is running, confirming operation. For air handling units, high static and low static pressure switches are both NC. The high static NC contact opens if duct pressure gets too high, shutting down the fan to prevent duct damage. The low static NC opens if pressure drops too low, indicating a fan or filter issue, and also stops the unit. Fire dampers use an NC contact as well, closed during normal operation, opening if the damper is triggered by a fire alarm, which breaks the circuit and shuts down the AHU for safety. Remember, NC contacts are used for safety interlocks, closed during normal operation, opening only on fault or unsafe condition. No contacts are used for status feedback, open at rest, closing to confirm equipment is running. Always wire these contacts in series for a true permissive circuit. If any NC opens or if an NO fails to close, the system will not run, ensuring maximum safety. Mastering the correct use of NO and NC contacts in these interlocks is essential for safe, reliable HVAC design. Get it right every time. Let's wire a classic chiller interlock. Goal: the chiller can't start unless both chilled and condenser water pumps are running and have flow. BAS commands each pump on. Flow switches in the discharge piping prove water is moving. The chiller's enable relay, CR1, is wired in series through both flow switches. BAS sends a chiller request, but the signal must pass through both flow switches before energizing CR1. If both switches are closed, CR1 closes its contacts, enabling the chiller. If either pump fails, its flow switch opens, CR1 de-energizes, and the chiller shuts down. This sequence ensures the chiller only runs when it's safe. No shortcuts, no guesswork, just solid logic. This is how you wire safety into every job. The right interlock protects equipment and people. That's a job done right, every time. Installing an interlock isn't enough, you must test it. Commissioning proves the system works as designed. Start with a visual inspection and wiring check. Use a multimeter to confirm contacts and connections. Test normal operation. Run the pumps. Verify flow switches close, then start the chiller. Confirm the system works under normal conditions. Now, simulate failures. Trip a flow switch and ensure the chiller shuts down immediately. Repeat for every interlock in the circuit. Label every relay and terminal clearly. Document every test. Create a checklist and sign off each item. This record proves the system is safe and functional. If it's not tested and documented, the job isn't finished. Testing is the final step in making it right. Never skip it. In the end, professionalism means making safety your foundation. Every action you take, every decision you make on the job, should be guided by a commitment to doing things the right way, not just the easy way. True professionals know that safety isn't just a checklist, it's a mindset that protects everyone in the building, from your team to the people who rely on the systems you install and maintain. Safety interlocks are the silent guardians of every mechanical room. They work behind the scenes, ensuring that equipment only operates when conditions are safe, preventing accidents before they can happen. Without them, even the most advanced systems can become dangerous in an instant. Cutting corners on interlocks is never worth the risk. A single shortcut can lead to costly damage, serious injury, or worse. It's never just about getting the job done quickly, it's about getting it done safely and correctly every single time. Always understand the control sequence, respect the interlocks, and never bypass them. Take the time to study the schematics, double-check your wiring, and confirm that every safety device is in place and functioning as intended. If a safety device is faulty, replace it. Never use a jumper wire. A temporary fix can have permanent consequences. The right part, installed the right way, is the only solution that keeps everyone safe. We owe it to our clients, colleagues, and ourselves to leave every job safer than we found it. Each completed task is a reflection of your integrity and your dedication to the craft. Share your knowledge. Teach apprentices why interlocks matter and how to wire and test them. When you mentor others, you're not just passing on skills. You're building a culture of safety and excellence that will last for generations. Passing on this knowledge strengthens the entire trade. When everyone understands the importance of safety, the whole industry benefits, and our reputation as professionals grows stronger. Next time you're in a mechanical room, look for the interlocks and appreciate their role. Notice how they quietly protect both people and equipment, and remember that your attention to detail makes all the difference. They let us control powerful systems safely and confidently. With every job, you're not just fixing equipment, you're building trust and ensuring peace of mind for everyone who depends on your work. The difference between a lasting system and a failing one is doing it right. Quality work stands the test of time, while shortcuts only lead to problems down the road. Your reputation is built on safe, quality work. Clients remember the professionals who put safety first and deliver reliable results. Make it safe, make it last, make it right. Every time you finish a job, let your work speak for itself. That's the mark of a true professional.